When we're dealing with graphing rational functions, ladies and gentlemen, what we're looking at here is we're graphing a polynomial divided by a polynomial. That's what basically a rational function is. These values of p's and q's is basically you are looking at a polynomial divided by some polynomial. It looks something along the lines as this. And you guys have seen this graph before. Y equals 1 over x. You've seen that. You've graphed that before. That is a rational function. All right? The number 1, even though it's a constant, it's still considered a polynomial. And obviously the variable x is a polynomial. So what happens here when we're talking about graphing polynomials, there are going to be specific rules that you have to follow in order to graph them. And what they've done is there's 2 types of functions that we're going to be graphing today. So there'll be 2 sets of rules. Thank you. There'll be 2 sets of rules here. And they're relatively straightforward. And you're going to see how it works. It's going to be blended from today. What we do today is going to be basically the same stuff tomorrow with a lot more complexity. So if I look at the graph y equals 1 over x, just to start with. If I look at that, what can't x be? 0. X can't be 0. Do you guys agree? Now, when you graph something, what do you put on a graph where something can't be? Do you remember this? Do you know this?
No.
Why do I make this a dotted line here?
So that
What is that called?
the origin, no clue.
You ever heard of an asymptote?
Same thing, man.
An asymptote. Asymptote. An asymptote. An asymptote is kind of like a boundary, if you will. It's what your graphs are going to approach, and they're going to get infinitely closer and closer and closer to, but it will never touch it. You've ever sat in the back of the car with a brother or sister saying, "I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you," for hours upon hours at end? Your parents wanted to throw something at you?
Like donkeys.
Like anything? Yes.
They threw me out of the car.
Right. Surprised they picked you back up.
No, I walked on.
So what happens here with these things is that there's asymptotes. And the asymptotes are going to be boundaries where the graph is going to approach. We're going to have vertical asymptotes, and we're going to have horizontal asymptotes, each depending upon what the graphs look like. And if you recall, as you went to start plotting these types of graphs, you guys always started by making tables. We're just going to pick some real easy numbers to work with here. If I pick 1, what's y? 1. If I pick 2, what's y? 1/2. If I pick 3, what is it?
1/3.
Okay. If I pick 1/2, what is it? 2. Very good. So basically, it's this curve. It's going like that. Every time you divide 1 by a smaller and smaller fraction, you're getting a larger and larger number. Okay. And then obviously, as x is getting larger and larger, the fraction is getting smaller and smaller and smaller. It's never going to reach 0. Same thing on the other side. If I choose -1, I get -1. If I choose 2, I have -1/2. If I choose 1/2, I have -2. And it's the same basic curve, just going the other way. Never going to be 0. Okay, it's never going to be 0. It's going to get infinitely closer and closer, but it's not going to equal 0 ever. It's because it's called an asymptote. Okay. So what we're doing here today is we're basically graphing functions that look like this. They're going to be mirrored over between quadrants, back and forth. When you plot these things out, and as we get into the little bit more complex ones, I'm going to ask you guys to label out your asymptotes. and give me sets of symmetric, or two sets of points on each graph. And as you get into these things, it's going to be really, really easy. Okay? So let's look at the generic form with h's and k's. We get this generic form of y equals a over x minus h plus k. And what happens here is that you're going to have horizontal or vertical asymptotes depending upon your h's and your k's. What's that? Yeah. Your vertical asymptote is always at the 0 of a denominator. It's always the 0 of the denominator. It's the h value. So it's at x equals h. And your horizontal asymptote is always at y equals k. And just like we've done in the past when we've dealt with a, h's, and k's, the easiest way to get going and setting yourself up for these is to label what your a, h, and k is. Because you're going to use them all the time. All right? So if I'm looking at this problem here, what's my value of a? -2. What's h? Is it 3 or -3? -3. So my a is -2, h is -3, and what's k? -1. So what happens here is that I know then if x is -3, I would get 0 in my denominator, and that would be bad. That's why there's a vertical asymptote at -3. That's what that means. You're finding the 0 of your denominator, and that is always your vertical asymptote. So let's look at this on a graph. -2, -3, -1. Same problem, looking at it graphically. First thing you do when you graph these things is you put your asymptotes in. My asymptote's at -3 and -1. It's probably a little clean. I'll shut this off. Let's see it. You see that better now? Yeah. So I have asymptotes at vertical asymptote at -3 and a horizontal asymptote at -1. Basically what we have done is we have moved the origin, the 0, 0, we've shifted it left and down. And now it's a matter of working with that value of a. So, how do you figure out your points? All you have to do is pick 2 points to the left of your vertical asymptote and 2 points to the right of your vertical asymptote and plot them. -4. -2 over -4 plus 1 minus 3. What's -4 plus 1? Sorry. Why did I write plus 1? Anyway, is that better? Sorry about that. What's -4 plus 3? What's -2 divided by -1? And it's -2 minus 1. -2 over -1 minus 1. So it's 2 minus 1.
You said it's -2 minus 1. Yeah, you said
Yeah.
-1. You're cautious today.
Must not enough. Anyway, so at -4, I know it's going to be at 1. Okay. What about -5? We do the same thing. -5 plus 3. -2 divided by -2. So at -5, it's 0. So we have 2 points, -5, 0, -4, and 1. See how these 2 points are going like that? That means my graph is going to look like this. No? What are the next 2 points on the other side? At -2, so we check it. -2 over -2 plus 3. -2 minus 1 is? And then oh, I just did the same value. You can do positive values, but what I want you to use 2 before and after.
Well, I mean, still be.
Yeah, you're still gonna get. I mean, you'll get there. And -2 over 3 minus 1, or excuse me, -2 over 4, so it's -1/2. Minus 1 is negative. So again, we're doing that.
Wait, should that be -1?
Yeah. Thank you. It's because I didn't draw it. I didn't rewrite this. I just wrote it over. There we go. So you have your 2 sets of ordered pairs now. And you get your graph. So we're at what? -1, -2. Okay. That's what we're looking at doing today. We're going to plot values that look like that and roll through them. Now, obviously, these are the simple rational functions. The difficult rational functions will be tomorrow. But you're going to still use the same basic premise. There's just a little bit more information. Right? There is another style.
Oh, there's smiley faces.
Sometimes the graphs look a little bit different. Sometimes they're in the form like that. Sometimes your graphs look like y equals ax plus b over cx plus d. What this looks like in normal terms, this. It looks like that. Do you see the difference between that one and the probably just graph? More numbers, okay. More specifically, notice how there's a value of x in the numerator and the denominator? Do you notice how there's no k value tacked on? That's why there's 2 types of problems we're looking at today. One with the a, h, and k, and one without. And it's very easy to tell the difference because you'll have a variable of x in both the numerator and the denominator of this style. The other one, you just have the one value of x. All right? So it'll be easy enough for you guys to decipher which one of these formulas I'm going to use. So here we have vertical and horizontal asymptotes again. Your vertical asymptote, I'll use this as our example. Your vertical asymptote is always the 0 of denominator. Okay? It's always the 0 of the denominator. And remember, if you're going to find the 0 of your denominator, all you have to do is set your denominator equal to 0. So what would be my 0 here? -3/4. So x equals -3/4 would be my vertical asymptote. Okay? That's how I find that. My horizontal asymptote is a little bit different for these guys. The horizontal asymptote is always the coefficients in front of the variable divided by each other. That's why they call it the A over C. It's these two guys.
In front of the x.
Yeah. In my example here, it's 2 over 4, otherwise known as 1/2. And that would be my horizontal asymptote. And again, it's okay to have fractional asymptotes. It's not a big deal. Not a big deal at all. If I wanted to look at this graphically, I'll split screen this here in a second and just get a graph up. If I wanted to do this graphically, just so you guys get the idea of what it looks like to graph a fractional asymptote, remember, you have an asymptote at -3/4. So that's about here. I mean, it doesn't have to be absolutely perfect. As long as you label it, stating what it is, yeah. I'll think again.
No, it's one of those students.
Oh, it's over there.
Here's one.
It's over here.
No, the little tiny stuff, last three, horizontal axis.
Oops.
It's like
Y A over C, it's 1/2. I was just putting this up as a split screen so we can graph it real quick, that's all. And there's your other one. Now, if I went to go graph, if I had to plot points after that, again, all I'm doing is just picking 2 numbers to the right of it and 2 numbers to the left. It doesn't have to be fractional amounts. I wouldn't use fractional amounts because that would just be a pain in the butt. You're still going to get some weird looking values, but that's how you start these problems. Okay? Again, there's 2 types of graphs we're looking at today. A, H, and K, where you just have a single variable of x, and then the other one with all the with 2 values of x, one in the numerator and one in the denominator. So let me walk you through another one. And this time we'll do it with domain and range as well. Do you guys remember domain and range? No. No. What comes first in the alphabet, D or R?
D is domain is X, range is Y.
Good. She's learned.
I'm not as dumb as I look, okay?
I didn't say you were. I just you remembered something.
Did we do this Friday? Shut up. He's happy for a chance that I learned Thursday. So
We talked about domain and range, yes, but we're looking at it in a different aspect today. That's all. So again, when I start these problems out, my vertical asymptote is always going to be my 0 of the denominator. So x can't equal what?
Two.
Third time's the charm.
Two. I wasn't right.
No.
X can't equal 2. If x is equal to 2, I get 0 in the denominator. Then it's bad.
Figure white girl.
Okay? So my vertical asymptote is at x equals 2.
I showed you Sorry, we're talking about our nails.
My vertical asymptote is at x equals 2. My horizontal asymptote is going to be at y equals what over what?
1 over 6.
What is it?
Half.
1/2. Yeah, 1 over 2. Since that coefficient is 1. Okay. So then I plot a fractional horizontal asymptote like that. So now I have my vertical and my horizontal asymptotes on my graph. Now it's just a matter of picking some points to substitute in. Again, pick 2 points to the right, 2 points to the left. 2 points to the left would be at 1 comma something, 0 comma something. 2 points to the right would be 3 and 4. Do you see how I'm just writing down my ordered pairs on both sides of the asymptote? Now all I have to do is just some simple substitution. What's 1 plus 1? Okay, so if I have x is 1, I get 2 over 2 minus 4, which is? So I get -1. Okay? So that means at 1, it's -1. At 0, what do you get? -1/4. again, since it's higher than the other one, it's going to be going like this. When it's 3, we have 3 plus 1 over 2 times 3 minus 4. That's 4 over 2, I believe. And when it's 4, we have 4 plus 1. Yes, sir. What's that?
Would that be symmetrical?
Symmetrical? Yes. Yeah. They're symmetrical, diagonally symmetrical. They're symmetrical about a line that goes through here that you don't know exists yet. I don't know if we talk so much about it. It's called a slant asymptote. It's kind of like a boundary that does allow the symmetrical amount of when it's twisted. When it's, I don't want to say twisted, but when it's an opposite axis or opposite quadrants like that, there is a line that goes through there. But we're not really going to get involved with that in this class. We'll talk more next year with that. Yeah. And let's see, the other one was at what? 5/4. So let's see, that's like 1 1/4. Again, there we go. And we've labeled out our points. Okay. Math that's not scary, I hope. What's that? What's wrong, guys? You get it? Is that it? Yeah, it's really all there is to this stuff. It's not that, it's, to start out with, I just want to get you guys the basics about how you identify your asymptotes and stuff. Oh, now we look at this again and figure out our domain and range. I almost forgot. Domain, think about it again. Domain is going to be all the values except for your vertical asymptote. So where's your vertical asymptote?
2.
So your domain is going to be everything except 2. What about your range? Everything except for 1/2. Very good. How do you do that? Well, when you're looking at your domain and range, your domain is going to be all but x equals 2. Yeah, you can write all as okay. It's implied that it's all real, and I'm fine with it. Your book writes all. Okay. And that's it. What were you saying?
Never mind.
All right. And same thing with the range. It's going to be all but yeah. Basically, again, your domain and range are going to be your asymptotes. Yes, sir.
Could you write like domain like not equal sign to 2?
What's not equal to 2 though?
Domain or x.
See what I'm saying? By just writing all but x, all you can write all not equal to 2, all x not equal to 2 if you want. So again, hopefully not so scary. Tomorrow when we get into more of this stuff, you're going to be having to, sometimes your polynomials you have to factor to find possible zeros, and there's going to be a bunch of different cases for your other style asymptotes. So let's try another one. Take a second and try this one. Again, state your domain, your range, your asymptotes.
It's just wrong. She's asking if you can write the domain for the last one, like x is greater than 2 and
X is greater than 2, x is less than 2. For domain? Yes.
It just sounds wrong.
No, you can write that. But you did not talk about the real stuff.
Yeah.
You gotta say all. And then obviously the ordered pairs I'm putting in there just to remind you guys to list out 4 ordered pairs, 2 on one side of the asymptote, 2 on the other. Take a couple minutes, see if you can get this one to go. Where is your asymptote?
That's
Down.
about the four.
Can I say it?
Yeah.
Okay. I do not have. Oh, there we go. 4. One is at 4. Yes. And then the other one is at 3.
Horizontal or vertical?
There's like a jump off.
Horizontal.
There's like a jump off.
So there are my asymptotes, which means my domain is all
Real.
x not equal to 4 and all y not equal to 3. Yeah, it's the 0. What's the 0 here? That's y.
Oh.
All right, remember, they're saying it is x minus h. That means h is 4.
But it's circle x.
Equals h.
Yeah.
H is 4.
Oh.
Remember the x minus h plus k, all that kind of stuff. How the h value is always that number. The k is usually flipped around. And k is dependent upon sign. Same idea. So that means I'm going to choose 3, 2, 5, and 6. When you substitute in 3, what'd you guys get?
4.
Good.
Great.
When you substitute in 2, what'd you get?
7, 9. Oh wait, they used to be like.
When you get 5, what'd you get?
2. But it like
6?
5, 2 halves.
2 halves or 1.5? Or 2.5. Hey, when you're writing those out, if you wanted to write it as 3.5 or 7/2, in the grand scheme of things, when you're not, it's not going to be a perfect graph anyway, because you're just kind of doing a halfway point here. So we're at 3, 4. Sure.
Wait, so you didn't have to do like if you do one on the right side, do you have to do one over on the left side?
Yeah, you have to pick 2 on one side, 2 on the other.
Well, no, like if you go like over one on the other side, do you have to do one over on the other side? Do you do 2 over each?
If you want, that's fine. I'm just saying it's easier to remember. Just pick 2 on one and the next 2 on the other. It's just easier, that's all. And then 5, 2. And 6, 2.5. And there's your graph. Okay. Like I said, today's stuff shouldn't be all that bad as you get into this. You should fly right through it. Tomorrow gets a little bit weird because there's a bunch of extra rules that'll happen. The same premise builds off of this stuff. Go through those. Don't forget domain, range, and I want, just like I did in that last example, get those 4 sets of ordered pairs, okay?
Are these all graphs?
The first couple of them aren't, just stating domain and range.
Okay.
The last one are graphs.
Where should we put those at?
You can just put those, you could probably put those on, like in the little middle column if you want.
Alright.
There's just a couple of them.
So,
Because the graphs, there's only what, 23, 25, 27, 29, 31, 33, 35. There's only 7 graphs, so you only need, that's why you only need 1 sheet. But yeah, the other ones, it's literally domain and range. I think it might ask you where your asymptote is. You might have a little bit of space there, or if you guys want to all take 1 sheet and split it, probably do that too. Okay?